Hi everyone, my name is Yongheng. I'm pursuing my PhD at Tsinghua University. I will be presenting our work, Shaping Data Distribution at Edge for Communication-Efficient Hierarchical Federated Learning. In this paper, we aim to improve the communication efficiency of federated learning with imbalanced training data. Federated learning is an emerging privacy-preserving learning paradigm, which enables cooperative learning of a global model at distributed computing nodes using local raw data. One of the challenges of federated learning is the communication overhead. Because the communication between nodes and the server results in significant overhead. Besides, it requires more communication runs when the node local data is typically imbalanced. And the increasingly complex model structures increase the data volume of model updates, both of which aggregates the communication overhead. But distributed nodes are usually constrained in communication resources, so improving the communication efficiency of federated learning is crucial. Existing works to improve the communication efficiency mainly follow two directions: reducing the size of messages communicated at each run or reducing the total number of cloud aggregation runs. For example, some compression schemes are applied to compress the model updates to reduce the communication message size. However, it suffers from information loss and performance degradation. Other works propose model update sampling and some algorithm optimization approaches. Differently, we investigate a hierarchical federated learning framework. One of the key insights of our approach is conducting model aggregations at the edge. That is, a subset of distributed nodes are selected as edge aggregators, which communicate with nearby nodes for edge model aggregations at low communication cost. After several rounds of edge aggregations, edge aggregators then commit model updates to the cloud for global aggregation. The merits are that the communication cost of edge aggregation is lower, and the hierarchical federated learning framework is easy to be integrated with existing works. We aim to minimize the total communication cost of hierarchical federated learning and define the following communication cost minimization problem. The objective is to determine the edge aggregator selection and node edge association to minimize the total communication cost between nodes, edge aggregators, and the cloud aggregator. The first constraint means that we cannot select nodes that can't play the role of edge aggregator. The second constraint represents that each node has to be associated with one and only one edge aggregator. In the last constraint, we limit the number of nodes that can associate to node aggregator E within BE. To solve the CCM problem, we propose an optimization framework share. There are two optimization directions toward solving the CCM problem. That is, minimizing the communication cost in each round of cloud aggregation and reducing the number of required cloud aggregations. Share first divides the CCM problem into two subproblems corresponding to the two directions and trade-off between two subproblems. Then it devises two lightweight algorithms to optimize the decisions of edge aggregator selection and node association respectively. The first subproblem is the per-round communication cost minimization problem, which aims to minimize the total communication cost in each round of cloud aggregation. We found that making the data distribution of edge aggregators more balanced could accelerate coverage, so the second subproblem is the KLD mean minimization problem, which aims to make the data distribution of edge aggregators PE closer to the uniform distribution PU. Then we trade off them using a parameter gamma. This is an NP-hard problem, so Share designs two lightweight algorithms to deal with the following two problems. The first problem is how to select a subset of nodes at edge aggregators. The second problem is, given the set of edge aggregators, how to associate nodes to them. Here, we first solve the second problem. That is, given the selected edge aggregators set, determine how to associate nodes with them. It can be formulated as follows. we need to determine the node association results Y. We devised the following algorithm. It greatly associates each node to an edge aggregator that can minimize the value of the objective function delta JNE until all nodes are scheduled. The first term of JNE is the communication cost. The second term is the average KLD reduction of associating node N with edge aggregator E. Then the algorithm finds out the association pair of N and E when the value of delta JNE is the smallest and associate them. We then focus on the edge aggregator selection problem to find the optimal edge aggregator set. We propose three types of operations to optimize the total communication cost: open E, close E, and swap. The algorithm repeats the three local improvement operations until no operation can further reduce the total communication cost. To evaluate the performance of share, we use two datasets with models, three network topologies, and comparing with three benchmarks. In the cloud-based FL, the nodes directly communicate with the cloud aggregator. The cost-only simplex and data-only greedy are two hierarchical federated learning benchmarks. The first one only considers the communication cost, but ignores the data distribution. It uses the simplex optimizer to find the optimal solution. The second one only considers the data distribution, but ignores the communication cost. Comparing with the cloud-based FL method, we can find that our method can reduce the communication cost significantly. Comparing with the hierarchical federated learning benchmarks, we can observe that share can outperform the other two benchmarks in all settings. Besides, the performance gap between share and the benchmarks becomes significant when reducing the cloud aggregation frequency. In summary, in this paper, we investigated the communication cost minimization problem under the HFL framework. We propose share to optimize the communication cost while minimizing the per-round communication cost and shipping it at edge. Finally, we proposed algorithms to make decisions on edge aggregator selection and node-to-edge association. For more details, please refer to our paper. Thank you very much.